In your career as an engineer, it is inevitable to come across a difficult topic or system that is not explainable in minute details. Take example, a computer. Very few people know all the details of how a computer works, from the physics level to the hardware level and software level of a computer. But is it necessary to know all the details of how a computer works to use it? It isn't necessarily essential to know everything about a system to use it. Many people drive cars around the world, but most do not know the intricate details of how the car runs, from the fuel conversion and exhaust to the turning system in a car. Not to mention now that we have autonomous cars. So as engineers and scientists, we need to be okay knowing that we won't know everything. It's difficult to know everything about a complex system, but is it necessary to know everything about the system to operate it? To drive a car, I don't need to be aware how it changes gasoline to kinetic energy. I simply need to know that if I press the accelerator, the car will begin to move forward. We can simplify this to a single action. Let's simulate the car as a box. So now that we have our box car, we can denote the pressing down of the accelerator as an input, denoted I/P, and we hope that the output should be moving forward. Another input-output pair would be the keyboard and a computer. You type on the keyboard, and characters should appear on the screen. Here we're creating a big table on inputs and outputs. Let's take this model one step further. Let's create a large list of inputs and outputs. Input is essentially, I do this action, and output is what I expect. We can continue to do this with a large amount of actions, but in the end of the day, if we do not change the box itself, we expect the same input to correspond to the output each time. Then instead of characterizing the system by what runs on the inside, we can just give a general idea of what input would correspond to what output. This type of technique is known as abstraction. Abstraction is a powerful tool that many engineers use to simplify a complex process or system. The simplified process or system is known as a black box, since you can't see what's on the inside, so it's black, because there's no light inside of a closed box. I think you get the idea. Once you are familiar with the idea, you'll notice that abstraction is everywhere. For electrical engineers and circuits, our black boxes come in forms of integrated circuits. These are essentially little black chips that have a ton of pins on them. These integrated circuits are very common and come included with them a datasheet that explains their purpose and their required inputs and expected outputs. These datasheets are dense and tough to read, but these are the design considerations that every engineer needs to look at to know what's best for his or her project. Integrated circuits are mass-produced through automation, are cheap, small, but usually only offer a few purposes at most. Of course, it begs the question why we need integrated circuits. We have all the tools to create chips with our passive and active elements. With digital logic, our combinations could create any system we need. Why buy something prepackaged when you can make the whole system yourself bottom up from the individual components tailored to your specifications? There are many questions to ask as an engineer, and this is the one that pushed us into a different world. Let's first tackle the issue why there are no general-purpose integrated circuits out there. If you look at your computer, you can also see that there are different modules that comprise your computer. You have a CPU, video card, Wi-Fi module, keyboard, mouse, and more. Yet although there's high demand for singular parts, which make it so difficult to create and choose a computer, people don't simply sell a huge chip with everything on that single chip. In other words, if I wanted a robot to bake some brownies, there are no chips on the market that will sell me a large chip that will fit my request. Which makes me very sad, because I'd want a brownie making robot. Looking at a high level, we can see that creating such a brownie making chip would be difficult. There would need to be so many parts within the chip with many inputs to that chip, like dough, sugar, eggs, and more. Having a general chip increases the complexity of the chip, the time to create it, and non-desirable hidden factors. Large circuits often come with the issues in managing heat since it requires a lot of power, and having a large chip makes it difficult to vent that heat. Not to mention, the market for selling circuits that can create brownies is probably very low, with a market of one, mainly me. Following the brownie example, it would be much easier to split the circuits into parts that could do singular tasks, such as mixing, baking, whisking, etc. By breaking the task into smaller parts, we can combine them to create what we want, a brownie maker. If we play our cards right and change a few circuits, we could create a cake maker, an ice cream maker. The possibilities are endless. This plug-and-play feature is known as modularity, in which we break apart things into smaller things that can run by themselves. Each component is known as a module, and they will work together to create something larger. Think of them as cogs in a clock meshed finely together. These concepts should help you understand some qualities and ideas engineers utilize to tackle difficult problems.